Okay, thank you. First of all, I'd like to thank the organizers and also the committee for receiving this FSA prize for this couple of papers on geometric measure theory. I'm very honored to about this. And in this talk, I will start from this work on geometric measure theory, and in particular on the regularity of minimal surfaces, and I will go further with more recent results, which are obtained with Paolo De Donato in Sapienza University in Rome. So let me start. The main theme is the one of minimal immersion. So let's assume we have an immersion M of dimension n in R n plus k. We can imagine, for example, without boundary. It is called minimal if its mean curvature, which is the trace of the second fundamental form, is equal to 0. So this one is a system of PDEs in the case where K, which we call the condemnation of the surface, is a single PDE, so to speak, which describe this concept. Now, why this concept is so spread in analysis and geometry? In part because of its variational nature. So the mean curvature, in some sense, is the first derivative of the volume of the submanifold. So every time we take a one-parameter family of deformation of our submanifold, so let's say phi t is the family of diffeomorphism generated by a vector field x with, say, compact support inside our variety, our immersion Mn. The first variation of the volume of this, which measure theory is the author of n-dimensional measures. The first variation of the volume along this one-parameter family of diffeomorphism is given by the integral of the tangential divergence of x, which after integrating by part, if x has compact support inside n, is really x times the mean curvature. So mean curvature 0 means a first variation of the area 0. So an immersion is minimal if and only if it's stationary for the volume. And this variational point of view is at the basis of its generalization. Because you have to think that in some sense we're interested into non-regular immersions. So the title was talking about the set of branch points, which are singular points for the immersion. And that's a very natural operation to do. And the point is that if you try to solve, to find minimal surfaces, like, for example, solving the plateau problem of minimal area with a given boundary, or else if you look at limits of minimal surfaces in a very weak topology, you end up with something which is actually not an immersion, not a regular immersion, even if you start from a regular immersion. But your limit will have singularities. So, for example, for those of you who were in the talk by Lukumovic on the Way law for the area functional, you see that the right context where to embed this problem is the one of flat chains, which are sort of a generalization of immersion. And here I comment a couple of these generalizations. One is the one which was called rectifiable integral manifolds. So n is always the dimension, Rn plus k is the space where they live. So a rectifiable integral manifold of dimension n is an equivalent class of couples m theta, where m is a set. So it's a set in Rn plus k, and this set is what is now called countably n rectifiable Hn measurable subset, which means that in terms of measure theory, so Hn almost all the sets can be covered by some manifold of dimension n. So there exists a countable family of some manifold Ci with dimension n, and for technical reason here the regularity class of this submanifold is C1, such that they cover almost all n. So that's what is meant by rectifiable set. And theta is a function, an integrable function on M, which when the value for this integral is with values to M. And now you see this sort of objects has a nice tangential properties, because almost every point in Hn belongs to a submanifold of dimension n. So almost every point has a tangent plane, so we can define the tangential divergence of a vector field. So as being stationary was saying that the integral of the tangential divergence was 0 on a regular immersion, we can assume the same definition for this weak notion of immersion. So a manifold is called stationary if and only if, for every compactly supported vector field, the integral of the tangential divergence in Hn times theta, which is called the multiplicity of the manifold, is 0. So that's a sort of generalized minimal immersion. So the equivalence relation is the one saying that M and M prime are so differ by a set of Hn measure 0, and the same for theta. So every time they belong, they are the same. And let me comment on the multiplicity theta. That's a sort of a necessary object there. We cannot avoid to have theta in this definition, because you have to imagine that minimal immersion can sometimes collapse one into the other, and the limit have the same support but reached by two of them. So multiplicity 2, minimal immersion is still a limit of objects in this class. So that's why we need both the sets and the multiplicity. And another notion, which is a subclass of the stationary manifold, are the ones which really minimize the plateau problem. So the solution of the problem with the least area. And these are called rectifiable mass minimizing integral currents. And the structure adds to the one of manifold, which is a measure theoretical notion. Here there is some algebra on top of it. So M theta are the same component as for an integral manifold. And then on top of this, we have to choose an orientation for the tangent plane. So meaning that so C is a field in with values in the n vectors of Rn plus k, which is the n exterior product in Rn plus k, which is defined like this. For almost every point, let's say, it's the wedge product of V orthonormal vectors, V1, Vn, and they need to form a basis of the tangent plane at M. So you remember that M is a rectifiable set, so almost everywhere coincide with a C1 submanifold. It has a tangent plane, so we have to choose an orientation of this tangent plane. So on top of being a manifold, we have an orientation, which is given by this n vector. And why this notion is suitable for finding solution to the plateau problem? Because for this notion, we can define apart from the notion of mass, which is the area, also the notion of boundary in a homological class. So we can fix the boundary. And the point is this: once we have an orientation, we can see these objects, the rectifiable current, acting on smooth n forms, which usually take smooth compactly supported n forms, which is the integral of the pairing between the n form, which is a field on the n exterior product in the contact band of Rn plus k, with the orientation we have by our definition, integrating over the manifold, which is theta Hn on M. And then once we have this, we have the area, the total area of the surface, which is the integral of the multiplicity, but we have also a notion of boundary, which is defined by the validity of Stokes' theorem. So the boundary integrated on an n-1 form is by definition the current integrating on the exterior differential of the form. So now we can talk about having fixed boundary. We can talk about the area, which is the mass. So a solution. The plateau problem is a current which has least mass among all currents with the same boundaries as the one we have. And for simplicity, we can also the variation to be compactly supported. So in this case, we have a notion of local minimizing. So this one allows to find minimal surfaces via minimization problem. The manifold are a good class for taking limits of minimal immersion. Now, so what is the point? We would like to talk about singularities of this object. So even if we start from something very regular, a minimal surface needs not to be regular. And here I give two very famous examples. So the first one is Simon's cone, which was discovered in 68. So as a manifold, it's a manifold with the multiplicity 1. It's supported on a set S, which is a cone given by this equation. So we are in R8, and I imagine the Simon cones like this. So let's put here the first 4 coordinates. Let's put here the rest set of coordinates. And we are saying that the modulus of the first set of coordinates, so it's 1 squared plus x4 squared, is equal to the modulus of the last 4. So schematically, we can draw the Simon cones like this. Of course, I mean, that's just a projection, a 2D projection. So this one is in R8, an object of codimension 1. So it's as 7 dimensions is locally described by an equation in R8. It's everywhere regular, except at the tip of the cone, where it is a singular surface. And in some sense, this one was the first example of codimension 1. So the codimension 1 relates to the relation between dimension and of the object and the space, which was found to be singular. And, and this singular in a very strong sense. It's the unique solution to the plateau problem with its own given boundary. Now you have to imagine if you intersect S with the boundary of the unit ball, in this picture would be these 4 points, so to speak. The only solution, the minimal surface which minimizes the area with this boundary, needs to be the Simon cone. So it needs to be singular in 0. Said differently, but still, I mean, I find it sort of significant. If you look at approximate solution, so what we call the minimizing sequence of minimal surface towards the minimum, this minimizing sequence in the limit, even if it is smooth, each element of the sequence is smooth, in the limit needs to converge to the minimal cone. So in some sense, this singularity is sort of an essential singularity. You cannot get rid of this. So given this boundary, which is perfectly smooth, 6-dimensional submanifold in R8, there is only one, in all the strongest sense, only one minimizing surface with this boundary. And the minimizing surface has a singular point, which is the origin. So that's the sort of singularities we are interested in, a sort of necessary singularity for these geometric problems, these geometric PDEs. And this one has as codimension 1 is concerned. In other codimension, so the situation is even more complicated. Because we can already find the 2-dimensional surfaces which are similar. And one of the examples are complex varieties. So for example, if we take a complex curve in C2, so it's a 2-dimensional real variety in R4, for example, the one given by Z3 equal W2, this one again is now it's real dimension 2 in R4, so the codimension is 2, it's bigger than 1. The origin is a singular point, it's not regularly immersed at the origin. And this one is minimizing by, so this one was a result by Bombieri and Giorgi Giusti. This one is a result by Federer, which is using identities produced by Wirtinger in the 30s. And also in this case, let me make a picture. Yeah. So everywhere, or almost everywhere, we give multiplicity 1 to these objects. and these are minimizing with this multiplicity. So they are examples, so to speak. So if I have to draw a schematic picture of this example, let me take a projection. Here I take the modulus of Z, here I take the modulus of W. I will draw this picture like this. So it's a two covering of the Z plane. And here you see, this one is not a regular point as a geometry. So here, our curve is not parameterized over the tangent plane, but it's a two cover of the Z plane. Now, what makes these two examples different? In some sense, the most evident difference is this. So the Simon cone has no tangent at the origin. You see here the picture is the one of the cone, and this cone is not flat. On the other hand, this complex variety at the origin has a tangent plane. So the tangent plane is the zeta plane. So it's the plane W equals 0. But nevertheless, this one is not a regular point, because this one is actually a branch point of this complex variety. So, so this very simplified, picture sort of explain why the strategy in studying this kind of singularities, rather than this, should be different. A common strategy in geometric measure theory is the blow-up strategy, which is not the one in algebraic geometry. It's exactly, it's the one defining tangent space. So we scale locally around the point. So we take our immersion, we look around the point P, so we translate in P, so we put the origin, and then we scale by homothetically by R. And we look at the limit of this point. Now, this equation, H equals 0, comes with the monotonicity formula, discovered by many people, De Giorgi, but now it's called Allard's monotonicity formula for stationary manifold, and the limit is a minima cone. And now you see, at point of the kinds A, the minima cone is not flat, and indeed the minima cone is singular. So if you apply this procedure to the Simon cone, it's already a cone, it remains itself. Whereas if we rescale this picture here, the limiting cone, it's the tangent plane, so it's regular. So here, this blow up, a regular space. So we start from the singularities and we end up with something which is regular. So the singularities disappear. In the case A, the singularities remains. Of course, it's not completely true that the singularity disappears. We have a trace of this singularity because we know that the tangent plane is assumed with the multiplicity 2. So this one is, in the case B, the two covering of the Z plane collapse one into the other. So here, in some sense, the main enemy here are points where we have a tangent plane, but they have higher multiplicity. So the strategies for these two problems, for codimension 1 and higher codimension, needs to be different, and indeed the results are different. So in the case of codimension 1, here I make a very short list of results. You know that, for example, in small dimension, all minimal surfaces, and let's consider the case of minimizing currents, which are the strongest notion, the most restrictive weak notion of minimal surfaces. In small dimension, they are regular, so they have no singularities. And the first singularity appears in R8, exactly as for the Simon cone. And indeed, this was a result made by the contribution of many distinguished mathematicians. In the 70s, Federer showed that the out of dimension of the singular set is n minus 7, which is so the out of dimension is a notion of dimension which is used in geometric measure theory. It means that the out of measure of exponent alpha with alpha bigger than n minus 7 is always 0, which is the case of the Simon cone. So the singularity is a point, which is a zero-dimensional set in a seven-dimensional surface, because the Simon cone is seven-dimensional. Much later, in the 90s, Newton-Simon proved that the singular set has also a structure. So the singular set, which is n-7 dimensional, is itself rectifiable. And we said what is rectifiable. It means that it's covered by C1 submanifold and the right dimension, which is n-7. And there was a recent result by Naber Valtorta in 1720s, where they showed that the dimension of the singular set finite. So single. That's, I mean, I think it's no. I think it's a no. I mean, I have no explanation. It's just as a matter of life. Yes, and this seven was in some sense discovered by Gene Simons, who studied it too. Exactly. Yes. This one, I mean, is the right measure for minimal surfaces. It was discovered by Simons studying uh, the stable cones in codimension one. Now, in higher codimension, so codimension bigger than one, the dimension of the singularity changes, and we had already an example. And this was really the great achievement of Ampere's big regularity paper. It proves that the out of dimension of the singular set is n minus 2, where n is the dimension of the current of the minimal surface, which is what we have seen for the complex curve. It's a zero-dimensional set in a two-dimensional variety. So this one is the optimal dimension. And in the papers which have been comprised with the FSA, with Camillo Dell'Ellis, we give a new proof of this result. So this result was a very long preprint, around 3,000 pages, which we revisit, and we gave a complete independent proof using these ideas of Andre in a series of papers, which the last two are the one which received this prize. A bit more is known for two-dimensional objects. It was a result by Chang in 89. The singular set is locally discrete, which is like you find here, really made of points. And with Camillo Dell'Ellis and Lucas Polar, we have been able to extend this to some cases where the current is not exactly minimizing, but almost minimizing, which is the case of semi-calibrated currents or the cross-section of minimal cones of three-dimensional cones. So the cross-section is two-dimensional, and also in this case, the singularity has locally finite measure, zero-dimensional measure. So it's locally finite number of points. And recently, there are results by Dell'Ellis, Minter, Skorobo-Kutova, and Krum and Vikrama-Sekera, proving that the singular set is actually rectifiable of the right dimension. So what is here the idea? So, yeah, yes. So that's the question I would like to discuss. I would like to know about the measure of the set, which in this case, in this case, I would say it's widely open. What is the measure of the singularities? Because this condition is a condition on the structure of the sets, being covered by countable many submanifold, but may still be of infinite measure. And that's the question I would like to discuss in this talk. But before arriving to this, let me explain so what is the difference between the approach, the usual blow-up approach, codimension one and denial codimension. And this one is a series of great ideas in big regularity paper. The idea is not to make an homogeneous blow-up, but they scale differently the horizontal and the vertical direction. So assume for a while that T is a multiple covering of a plane, like in the example we have. So the idea is now to rescale different the z variable and the y variable in order not to keep the area like for the homothetic, so not to keep stationary for the area, but stationary for the Dirichlet energy of discovery. So, for example, that's just, an explanation by examples. So, in the case of the complex varieties we've considered up to now, we rescale Z by R, and then W we rescale by R to the 3 half. So this rescaling is keeping the Dirichlet energy, and indeed, if you look the homogeneity, this complex variety remains fixed under this rescaling. And the singular points remains there, and in the end, what you get is a minimizer for the Dirichlet energy. I'm going to, to say something more about this. And this one is sort of the strategy. So not blowing up to a stationary cone for the area, but blowing up to a minimizer, a stationary profile for the Dirichlet energy. Now, this idea has a major difficulties, which was the one we faced in the first paper, which have been awarded this complex, which is that also this kind of rescaling can make singularities disappear. So take this slightly more complicated complex curve. So W minus Z squared all squared equals Z to the 5. Again, if you want to picture this complex variety in this schematic way, so I see this as a W is a sort of a branch over a regular complex curve. So I take the complex curve, so W equals Z squared, and then on top of this, I'm adding a branching like 5 half. So the real branching is a perturbation of this. So now if we make the rescaling here in a way to preserve the Dirichlet energy, you realize immediately the only possible rescaling is this. Z divided by R, W divided by R squared, which is ending up again in a regular curve. So the blow up, even in this non-homogeneous rescaling, is still regular. And again, is a multiplicity 2 regular object. So the idea of Avogadro, this point was to construct what he called a center manifold. So the center manifold should, morally speaking, should be the average of the branches of over a regular object. So in this very simple example, so schematically we can write the two branches like Z squared plus minus the square root of Z to the 5. We take exactly the average of the two. The average of the two is the red part in this picture. So what we do is we do not parameterize over the Z plane, but we do parameterize over this center manifold. So parameterizing over this center manifold, we have now that our perturbation is the square root of Z to the 5. So schematically written like this. So if I blow up this, now the rescaling changed, and I still see my singularity. Because if I blow up this, I end up with the same. So the strategy of the proof was, you have to imagine this very nonlinear setting of geometric measure theory, was to construct a center manifold and then performing a sort of inhomogeneous blow up over the center manifold. And then from there to conclude. Now, this one is more or less, so the strategy in Amten's paper, and is so what we reworked in these papers. Let me also say, if instead of minimizing we go to stationary, much less is known. So basically, only Allard's regularity theory, which says that the regular set is a dense open set. So singularities are a nowhere dense set. And in some sense, so one of the main difficulties here is encountered by these points where the singularity has a flat tangent plane, which are typical of higher codimension or stationary immersion, which are not minimal. So this also happened in codimension 1 when we drop the minimizing hypothesis. So moving from this, I would like to address this one, which is perhaps the most challenging question at the moment, in this field, which is the one on the measure of the singularities in higher codimension. And in particular, in higher codimension, we look at the measure, for example, these points. Because even if, so the recent results by the Lellis collaborators, Vikram Sekera, Krumel, proves that they are rectifiable, still they leave open the question about the measure. And what we consider this paper with Paolo De Donato is a case study. So, which is the case of a stationary graph of a two-valued function of regularity C1 half. Now I will come to this, but it's a case study which is modeled on this example. And this one was a case which was considered in a recent paper by Neil Simon and Luciano Di Framasekera. They were interested to study singular point of stable, so not minimizing stationary variable, where the density is strictly less than 3. For us, the main motivation was testing this conjecture. Yes. So yes, theta less than 3. We wanted to test this conjecture in this simplified setting. So I have to introduce this setting. So I will spend some slides on this. So the dimension are general and dimensional K codimension. And we introduce the space of 2 points, which were already introduced by Arnold in his big regularity paper. They are the set of points P1, P2, where we do not distinguish the order. So we like to imagine it as a set of measures, so Dirac deltas, atomic measure in P1, P2. So the measure is a unifying object, whatever the order of the points I give to describe it. Or in a combinatorial way, you can imagine as the couple of points P1, P2 modulus the relation given by the permutation. So the couple P1, P2 is the same as P2, P1. This one is a metric space. You can put many metrics. This one for people in calculus of variation is known as the Wasserstein distance with the exponents 2. So you take the optimal couple, you have P made by P1, P2, S made by S1, S2. You take the optimal couple, P1 with S1, P2 with S2, or P1 with S2, that's S2, sorry, P2 with S1, and you optimize the Euclidean distance between this permutation. And now a two-valued function is simply a function having valued at these 2 points. So let me explain you why this complication here is needed. And the point is understandable from our example of a complex variety. So let's remember it's W2 equals Z3. So this complex variety has the topology of a disk, even if it is a double covering of the plane. So if you start from a point on this up, an S1 on the Z plane, you will end up continuously on the other branch. And then if you follow again another Z1, S1 in Z, you will end up again up here. So if I have to distinguish which couple of points I assign to Z, which is plus the square root of minus the Z root, the square root of Z to the third, I cannot make this distinction in a continuous way. So there is no between one determination of the square root and the other. Because every time I go around the origin, I change the order of the square root. So that's why we need to have a notion of a function with value which takes a definitive numbers of values, this case 2, but we cannot distinguish about the order if we want to have a sort of continuous selection of these things. And of course, this space, it's a singular space because of the action of this quotient with the action of permutation. So we are looking at at maps with values into a singular space, which is a singular cone in an Euclidean space. But it's sort of needed because we can not distinguish one branch from the other in a consistent way. Now, to such functions, we associate a variable. We just look at the graph. So the point x, ui of x when I is 1 or 2, and then we assign multiplicity 1 if the 2 points are different, and we may say multiplicity 2 if the 2 points coincide. So this one is, so especially if u has some regularity, this one is a variable, and the regularity we are assuming is a sort of strong regularity, which is this C1 alpha. So let me explain what we mean by C1 alpha regular. First, I have to say what we mean by differentiable for such maps. So a map is differentiable in a point if we can find two matrices such that the linear function ui x0 plus mi x minus x0 approximate our function u. So for each point, for example, every point here is a point of differentiability because if I fix my x here, for u1 of x, u2 of x, which I don't know what they are, I can associate the linear part. So let's say that's x naught, and the same here. So they have a well-defined linear part which approximate in our distance g like a little of the distance of the points. But also the origin is a point of differentiability. Because in this case, u1 and u2 are the same, and I take m1 equal to m2 equal to 0. So the linear part, the origin, is a multiplicity 2. So these two parts coincide here with the multiplicity 2. So this one is a point of differentiability. So it's easy to see that these MIs are unique time where they exist. So I may call them the differential of UI. But remember, UI, it's not differentiable. It's not even locally defined in some sense. But once they exist, by definition, I'm associating MI to UI. So as a notation, I call this gradient of UI. Even if UI may not be differentiable in the standard setting, and I can consider the couple UI gradient of UI, which now it's a function with two values in this larger space. So since the space of 2 points is a metric point, I can define continuity or the continuity. So when this function is order continuous, I say that U is C1 alpha. So a function is C1 alpha, like in this case, when we have a continuous dependence in some sense of U and of the tangent plane associated to U. So to such a function is associated variable. And so last slide of notation, I introduce, we call a map U stationary when the variable associated is stationary. UI is the average of the two branches, U1 plus U2 half. V is the symmetric part. So UI is a RK, a normal valued function with one value. V is still a two-valued function, which is now symmetric. U1 minus U2, U2 minus U1. Which is in some sense what's happening here. So the average is the red part, and then the branches are the symmetric parts on top of it. Z are the points where are the 2 points. So where the symmetric part is 0 or where u1 is equal to u2. And now we come to the definition of singular points, is the boundary of the 2 points in omega. So why the boundary? So let me also explain this notion here. So we look at a regular point, the singular point, from the point of view of differential geometry. So if our object is embedded or not embedded around this point. So it may happen that the minimum surface has a smooth part with multiplicity 2. And this one for us is a regular part. Even if it's a double point of double points for our graph. At the boundary of this double point, where we finish to be two valued, and then we have two branches with one value. So this one for us are the singular points. So not all the 2 points are singular, because they may have multiplicity 2 collapsed on a regular surface. So this one is fine for us. But the boundary of the 2 points, they are in our singular set. And last definition, the singular set we divide into 2 parts. We may have the self-intersection, what we call the IU, the set of intersection points, which are the points where so they are not regular from a differential point of view, because there our function is not a manifold, like the intersection of two disks. So for example, for the function z minus z, which is the one I put here, this one is a singular point, because it's on the boundary of the 2 points. But it's around this point here, the surface can be divided into regular minimum surfaces which intersect at this point. So this one are where 2 branches intersect transversally. So we can consistently talk about U1 and U2. So selecting the 2 branches. The branch points are the points where this does not happen. And the main example is our favorite one of the branch points here. Here there is no way we can cut in 2 parts producing 2 smooth minimum surfaces. So cut will be discontinuous in this case. So that's the set we are interested in, the branch points. And what are the results? So let me start from this very nice paper by Simon Vikramasekera. So they show that if you start from a C1 stationary map with 2 values, then so alpha is any number between 0 and 1, then the average is C11. And the symmetric part has regularity C1 1/2. So even if you were starting from alpha equal 1/10 a priori, actually U is more regular, and that's the average, which has a derivative which is Lipschitz continuous, C11, and the symmetric part is as derivative which is order continuous with the exponent 1/2. And these 2 exponents are sharp. And in fact, the C1 1/2 we see from this. So recall. So this variety for us is the map which is sending z to the determination of the 2 square roots of z to the third. And you see that z to the third is derivative, which is square root of z. So the derivative order continuous with the parameter 1/2. So better than 1/2 it's not possible in general. So this one is the sharp regularity they prove. And then they prove that the branch set has out of dimension which is at most n-2. So which match with the n-2 by Hamlet for minimizing cut. So what we prove with the Paolo De Donato, the very same setting, we prove that the measure is finite. So we prove that the measure HL-2 is locally finite, so finite on every compact set in our domain omega, and the set is also rectifiable of the measure n-2. So that's our result. Okay, let me point out that these graphs of functions are in general not not mass minimizing, but they are only stationary manifold. So strictly speaking, this case is not included in the big regularity paper. Of course, I mean, the geometric assumption are very strong because we are assuming to have a graph and actually a current has not such a decomposition, even as multiple value graph. And I mean, especially having two values limits to the set of points with a multiplicity less than 3, as I mean in the case of Simon. Then the rectifiability part of our statement was also proved with different techniques by Krumer and Vikramasekera. But as far as I know, there are no results on the measure, so whatsoever in this higher dimension. So this one is a sort of a case study for the measure of the branch set under our point of view. And what we obtain is an estimate on the Minkowski content by Naber, Valtorta, in coordination 1. So a bit more refined as the out of measure. So the tubular neighborhood of the branch point has locally a measure which scales like R squared, which is the typical scaling of a neighborhood of a set of dimension n-2. So if you take a curve in the plane, and then you take an R neighborhood of this curve, the volume of this neighborhood scales like R, which is also giving something about the structure of this branch set. So I planned to say also something about the proofs, but I want to be, my time is basically over. I want to be very, 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 very quick, just to give you a glimpse of the techniques. So not more. Then if you have a question, we can discuss later. And I divided in parts. So one part is writing the variation of this function. So we take the area function, which for these two valid maps can be written as the sum of two how they're called, I mean, polyconvex integral, so the usual area integral for graphs in high dimension. And then we take the derivative, the usual Euler-Lagrange equation for this, which is the one I've written here. Now, if you manipulate this identity a bit, you end up with a sort of a linear system of PDA. Of course, you have put all the non-linearity in this coefficient, A of x and L m of x. Just in some sense, I mean, defining as a function of x, the non-linearity coming from the system. Now, what is the characteristic of this system? Is that the principal part is a second order system of PDEs. The principal part is in diagonal form. So A of x is the same for all the branches and all the coordinates. And coming from the result of Simon-Wickrama-Sekera, this coefficient have a certain regularity. So A of x is Lipschitz continuous and L is bounded. Lipschitz continuous coming from exactly this 1/2 in the results. So it's sharp. If V is C1/2 come with estimates, then this coefficient is Lipschitz. A coefficient less than 1/2 wouldn't give here Lipschitz. And this L infinity comes from C11 of the average. So a bit less than C11 doesn't give this L infinity. And why I say this? I mean, especially for the Lipschitz part of A, because it's well known, there are results in the 80s by Garofalo and Lin, that when the metric is Lipschitz, this system of equations have unique continuation properties, which you can state in terms of the frequency functions. So the well-known Amundsen frequency function is true when the equation is Lipschitz coefficient at first order. And this one is the monotone quantity, which were sort of replacing the monotonicity formula by Allard. So thanks to this frequency monotonicity formula by Allard in this version of Grofolo-Lin, but was used the same by Simon Vikramatsekera, you can make this non-homogeneous blow-up. So once you have a non-homogeneous blow-up, you have doubling estimates, you have also the characterization of the blow-ups, which are homogeneous functions like this. And then you have, by Andre-Federer reduction argument, you have a dimension, an estimate of the dimension of the branch points. So how can we gain the measure? So what we do in our paper is the following. Instead of taking that natural frequency, which is coming from the Euler-Lagrange equation with variable coefficient, we take the usual frequency, which was introduced by Andre for an harmonic function. So no coefficient. It's a ratio between the Dirichlet energy and the L2 norm of the boundary. But once we know that we have doubling estimates coming from the previous frequency, we know that also this frequency is almost monotone. For points where the matrix at the origin is the identity. So the equation at the origin is the Laplace equation, so to speak. Why we use this frequency here? Because now that we have no coefficient, we can take the derivative in x. So these balls are centered in x. And taking the derivative in x allows to have an estimate on the oscillation on the base point of this frequency. An oscillation which is estimated by the square root of the radial oscillation at the points. So this estimate is the one which is behind this result. We cannot use this estimate the way it is, because in X, our matrix is the identity, but in nearby points, the matrix cannot be the identity. So we have to take one more step. We take a sort of a new frequency, which we call the intrinsic frequency, which is defined at every point X after change of coordinates, which depends from point to point. So this one should be so psi of x0, and the same here, v of x0. So at every point we change the coordinate to have the identity, we define the frequency for this changed coordinate, and then we go back, and we can have a similar estimate as before for these intrinsic estimates. Now, for this intrinsic frequency, we can use also the monotonicity in the radii, because now this one is monotone, because at every point I fix the matrix to be the identity. And using the spatial oscillation and the monotonicity of the frequency, I can conclude. And the conclusion goes back to the argument that Nabre-Bartorta introduced in codimension 1. So an estimate on the mean oscillation of a measure by the radial oscillation of the frequency. So once you prove an estimate like this, you are in position to use all the machinery by Nabre-Bartorta, which is a very beautiful piece of work, which can give you the rectifiability at the local finiteness of the measure. And that's the way we conclude. So I thank you for the attention.
Very nice talk. Are there any questions, comment? Well, that's it. I couldn't understand that the last step from the inequality to say rectifiable. That's kind of big theorem by neighbor.
This one is a big theorem, yes, and it's used in this way. So the structure of the equation is able to say that the oscillation of, so the mean oscillation, which is
Right.
defined like a sort of the L2 norm of the distance of the support of a measure, say of a measure with respect to a plane of the right dimension. So we look at the plane of dimension n-2, which is the dimension of our singularities, and we optimize among these.
Right.
We apply, so we consider these objects when mu are measures supported on the singular set, on the branch set.
Right.
And now, so the fact that we can control this oscillation by the oscillation of the frequency implies that we control a series of these beta numbers.
Right. The
By
frequencies are you introduced, right?
Yes, this one are the one we introduced.
Oh, okay.
Now this one is our dyadic series. I mean, you can jump from 4 to 1 dyadically. So once you have monotonicity, you know that here the sum is finite.
Right.
So you end up with the condition of the finiteness of the series of beta numbers on dyadic on dyadic sum. And this one is a condition, can be used as condition for rectifiability or for controlling the measure.
Oh.
Because this one is a sort of saying that the singular set is not deviating too much at all scales, does not deviate too much from n-2 dimensional planes. So making all of this quantitative is this very big work by Neber-Bartol.
When that was proved, actually?
So around so 16, 17.
Oh, all the results.
Yes.
Do you remember how to?
No, 2016.
Oh, 2000, right.
Yes, 2017. So.
Oh, do you remember how they can find those countable many manifold or something?
You follow this sort of this optimizing planes.
Okay.
So at every scale, around every point, you have a plane which is approximating this support of the singularities. And if you patch all these planes all together using ideas coming from Reichenberg-Disk theorem, if you patch these planes together, you track this C1 sum manifold which will cover your singular set.
I see.
So that's so for us the point. I mean, having this machinery. So the point was to reach the right estimates in order to start this procedure, which is due to that.
So is it impossible to say you have finitely many submanifold outside maybe outside dimension?
No. At this point, no, because it's really an argument in measure theory. So you need covering, you need to take away set of small measures, and then iterate infinitely many times the covering. So, like in measure theory, immediately you end up with countable many objects. That's
Thanks. Yes, please.
Just now you drew a picture of Simon's cone, and I'm wondering how many minimal submanifolds do you have with the boundary given by the truncated cone?
Only one.
Only one?
Only the Simon's cone.
I mean the minimal. The minimal.
So not minimizing.
Not necessary.
So if you, of course, I mean here, changing the definition, I mean things a bit changed. But if you, for example, stay in the setting of rectifiable currents, even if they are not minimizing, but they are just minimal, there is just one, which is the Simon cone. So to say that, I mean, that sort of singularities is really necessary. So the same happened with this curve. So there is just one, and it's this. And the argument is a very nice geometric argument. I mean, for example, for the Simon cone, you may foliate the way how it was proved by Bombieri and Giorgio Giusti that this one is minimal. You may foliate your 8-dimensional space by minimal surfaces, leaves which are regular minimal surfaces except for the Simon cone. A foliation like asymptotic minimal surfaces like this, but in array, you have to imagine this one is a single one.
Yeah, this is a hard Simon
Yeah.
formation.
And also like this. So now start from your boundary
Oh,
here.
I see. There were some.
By the
contact
maximum
point.
principle, you cannot touch any one of the foliation. So you need to be exactly this. So these sort of singularities are really, I mean, inside the problem, naturally inside the problem. But,
Thanks. And another question is about your result and also and
Vikramasakera.
result. I guess the dimension control is only taking for the interior part or for some interior part of the graph.
Yes.
Is there some boundary version?
Not that I know of, not yet. So the result is really only on the interior part, and it's compact subset of so on the interior part, so not global result.
Thank you.
You're welcome.
Any other questions? During his break, maybe. Oh, let's thank the speaker again.
Thank you.